Okay, so this is the YouTube presentation for the Physics 116 final project. This is a project for Trevor Brown and Anna Card-Larson. So this single video includes both of the assignments for the final project, and tacked on at the end is the additional extra credit project. So the first one is the speed of sound measurement. So I did this at a tennis court near my house. I looked up that the length of a tennis court is approximately 23.77 meters, and I was sitting kind of beyond the length of the court, and the wall that I was echoing my claps off of was also like beyond the length of the court, so I approximated that like the total distance was about 30 meters. Um, so you can see here that I did 3 trials total. What I did is I kind of timed the number, or I counted the number of claps over a period of 20 seconds. So for trial 1, there were 55 claps. For trial 2, there were 57 claps. And for trial 3, there were 56 claps. And so across these 3 trials, for trial 1, I measured the speed of sound to be 330 meters per second. Trial 2, 340 meters per second. And trial 3, 336 meters per second, with the total average of 336 meters per second. The total error that this represents is 2.04%, and this is based on the literature value for the speed of sound of 343 meters per second. This next slide includes some of the calculations of how I arrived at these answers. So for the calculation for each of the individual speeds of sounds, you can see here this is for trial 2. So I had 57 claps in 20 seconds. Since the length of the court was 30 meters, this sound had to travel twice that, so from my hand to the wall and then back, so I had 60 meters there. And since each clap was half, since I guess the echo is occurring at half intervals of each clap, I multiplied that total value by 2. And so, and you can also see that the units here are canceling, so like the units of claps are canceling, and so my final units are meters per second. The next bit here is the error calculation. And so I have my average of the speed of sound like that I empirically determined, minus the literature value of 343 meters per second. So I took that absolute value, divided it by the literature value, and times it by 100. And so that gave me the 2.04% error. And so for the discussion here, I was asked to comment on whether this value was consistent with the actual speed of sound, and it was within 2%. Some modifications I could do to this experiment would be to record my echoes over a larger distance. Sort of like the shorter distance would naturally will increase the amount of error, because I can't really, because when I'm measuring over such like a short interval of time between each clap, there's naturally going to be error on like either end of it. And also increasing the total time interval would also decrease the error, or also decrease the error. So if I record a claps over 60 seconds rather than 20 seconds, I would expect that my empirically determined value to approach the literature value of the speed of sound. And so for the next project here, we have the beat frequency of 2 pendulums. So I chose the beat period between them to be 22 seconds, just kind of arbitrarily based on the ones that you gave us. And so what I did is I chose the first period kind of randomly. I wanted there to be 11 periods chosen for the first pendulum, or the first L, and this yielded a frequency of 0.5, I guess like rotations per second. Through my calculations, which I'll show later, this led to a length of 0.993 meters, total length of that first pendulum. In order to determine the beat period, I chose the second length to represent 12 periods, which yielded a frequency of 0.54 sort of rotations per second. And so through my calculations, that I'll also show that this represents a length of 0.851 meters needed to achieve this frequency. So you can see my calculations here. The relevant equations that I used was our basic frequency equation. So F equals 1 over 2 pi times the square root of the unit of gravity, so 9.8 meters per second, divided by the length of the pendulum itself. And so going through here once again, L1 was 0.93 meters and L2 was 0.851 meters. Here is a video representing this. It's about 30 seconds long, but you can see where it's time stamped on when I first initiate the first pendulum moving, or when I initiate both of them going, that they will be out of phase initially, but exactly 22 seconds later they will be in phase once again, which represents the beat period that I was going for. There it is. So they're exactly out of phase right now, and here they are approaching in phase there. And so that's exactly 22 seconds based on the timestamp. The next question I was asked to answer was whether I could use a different length for a third pendulum. And the answer was yes. And so what I could do is this would be achieved by decreasing the frequency of that pendulum. And so instead of 12 or 11 periods per second, I would do 10 periods over the interval of the 22 seconds. And so here this represented a frequency of 0.455 hertz. And so the length for this, since it's a lower frequency, it would have a longer length of 1.2 meters. So moving on now to the extra credit assignment. So this is the coupled pendulum. And so to start off, I'm going to show a video of the system that I created. And so you can see here, which I'm going to explain in a second, that they are oscillating in and out of phase. Since each of the pendulums is the same length, they have the same natural frequency. However, based on the fact that there's a length of string in between them, when one starts going, when one starts rotating back and forth, it exerts a force on the other pendulum, which causes it to start moving, and this causes like back and forth relationship, and so their amplitudes are oscillating kind of in opposite directions of each other. So here's the explanation of that. So yeah, I think the key point here is that since they are the same length, they have the same natural frequency, and so yeah, once again, their oscillations are in opposite. And so you can see that for the right one, for example, it reaches its maximum amplitude and then goes to an amplitude of 0. And then when that pendulum is at its amplitude of 0, the adjacent pendulum is at its maximum amplitude, and they kind of go back and forth in that direction. The next example here, well, I'll just start with the explanation. The first pendulum is longer and therefore has a slower or like a lower natural frequency. So the induced vibration, so this first pendulum causes an induced vibration on the second adjacent shorter pendulum. So it's about, I think it was about like 10 centimeters shorter. However, since the natural frequency of the second pendulum is much faster, it does not have a significant effect on the frequency or really like the amplitude of the first pendulum. And so you'll see in the video in a second here that the first pendulum maintains a relatively constant amplitude, while the second shorter pendulum's amplitude oscillates between having no amplitude at all and having really like its maximum amplitude. So here's the video for that. Yeah. So you can see the longer pendulum maintained its amplitude while the shorter one, its amplitude oscillated back and forth. Okay, so that concludes all of the assignments. If you have any questions, please let me know. Thank you.